Hey everyone, and welcome back to the EdgeVerse Techcast, your go-to spot for all things embedded systems, software, tools, and enablement. I'm your co-host, Bridgette Stone.
And I'm Kyle Dando. Today's episode is going to focus on a technology that's becoming increasingly important across multiple industries. That includes, but is not limited to, agriculture, public safety, package delivery, and robotics. Bridget, do you have any guesses on maybe what we're talking about? What if I was to add really amazing light shows?
Oh, Kyle, you shouldn't have given it away. Obviously, this is drones.
Yeah. I like to give you a chance. Now, when most people think about drones, they immediately think about cameras, the sensors, and the AI that are on board, or maybe they even think about those light shows I mentioned. But none of this really matters if those crazy drones can't communicate reliably.
Exactly. Every flight command, telemetry update, video stream, and safety message depends on a wireless link that has to perform in some pretty challenging conditions. And unlike your smartphone or laptops, drones are constantly moving, changing distance, encountering interference, and in some cases, operating far beyond visual line of sight.
So what does it actually take for you, the listener, to build a communication system reliable enough for these professional drone applications? Well, that's what we're going to hopefully tackle today. How does it differ from your hobby drones? Why are developers looking for something other than just those traditional wireless technologies that you see around the house? To help us answer these questions, I'm not alone, Bridget. I'm joined by none other than the wireless communications expert, Wim. How do you say your last name, Wim?
Rouwet.
Okay, so thanks for joining us today, Wim. Why don't you start by telling our listeners a little bit about yourself and what are you doing here at NXP?
I've been with NXP forever. I actually started 25 years ago and what used to be called Motorola Semiconductors, and then made my way through what then became Freescale and got acquired or merged with NXP. In that experience, I've been all over the world. Started in Germany, went to Scotland, and now I'm based in Austin with you. Over time, I've always been in telecom and compute. I started, I'm showing my age, I started in WiMAX and 3G, made my way through 4G infrastructure, and now in 5G. And together with, data center compute type topics. This is interesting. I'm an engineer by trade, but more and more talking to customers on the marketing system definition side. The systems architecture thing is primarily, let's say, drawing block diagrams with fancy crayons and PowerPoint, figuring out what does the hardware chip needs to look like, what are the software stacks that run on top of the chip. So yeah, still having fun.
I've seen you at customer calls. These are not crayons you're using. I mean, you're meeting with some pretty top customers. You're hearing about all their requirements. And as you said, you need to develop not only the chip, but all the software that's allowing these people to innovate.
Yeah, Wim, thanks for being here. And we like to start with an easy question for you. When most people think about drones, they probably think cameras, motors, batteries, or AI, but communication is really a lifeline of the entire system. So what makes drone communication so challenging compared to other wireless devices?
One of the key things is the reliability of the link, right? And there's a little bit what Carl was going in earlier. Why is this different from the Bluetooth link to your headphone? Is the drone line needs to work all the time. And in fact, there's more than just one communication link. Consider, for example, you have a video stream from the drone down to planet Earth to the controller that has a different bandwidth. It's a video stream compared to the link from the controller back to the drone, which is fundamentally up, down, left, right type stuff. The key is if either of those links break, where does the drone go? that makes it challenging, right? The answer to your question. As we said, we live here in Texas, and we've got a kid that has a drone. If the link breaks and you need to chase half a mile in summer after your kid into a forest with snakes and stuff, you understand that reliability is super important to you.
You just have to buy a lot of drones because nobody's going to go search for that thing.
Or even worse, you're having to chase one of the lost drones crashing down on a stranger's party.
I have been there. The good news was that the stranger had beers, so it worked. The thing is, we kind of talked about use case here, right? There's always the use case that drives the engineering requirements. And a drone also travels in a different way than a human that is walking. So now we're getting somewhere. Wi-Fi was fundamentally designed to work at pedestrian speeds. Wi-Fi does work at faster speeds, but it's indoors, limited range, not really doing handovers between different access points and stuff like that. Whereas a drone can fly at an extremely high speed. I think top range drones are like 700-800 kilometers an hour. At that speed, the Wi-Fi waveform doesn't really work anymore. Consider that between the drone and the operator, there's what's called a channel, the air between the drone and the operator. And if you travel at a super high speed, that channel changes quickly. Like if you go around a tree, the RF path between the drone and the controller changes fast. That's where Wi-Fi doesn't cut it anymore if you're dealing with these slightly higher end drones. That's just one example. Wi-Fi doesn't necessarily do it for that type of reason. Then you could go like, well, why not connect through 5G? Your favorite operator, your Verizon, AT&T, T-Mobile type setup, just connect a 5G modem to a 5G operator, but they may not have connectivity. There are plenty of places in West Texas or towards Mexico where you definitely want to deploy drones or oil searching or rescue operations, whatever else. Okay, operator might not have a working network. Then you can think about a private 5G network. We have customers that are in the security business that basically want to deploy a private 5G network around the campus, like the NXP office here, and fly around drones in a self-controlled network. Then you're stuck with an outdoor network that needs to work all the way indoor, 14 cubicles inside. So all these things make the drone communication different, special, more difficult. And those are, at least to me, somewhat novel. Where you see a lot of people doing different things. There's not one universal way to control a drone or to communicate with a drone.
Are the requirements different between like a hobby drone flying around a park and a professional drone being used for inspection or agriculture, public safety, or delivery?
Yeah, absolutely. The hobby drone flying around a park is typically, because hobby means cheap, many a time controlled still with Wi-Fi. There are those low-end drones that are fundamentally there to take pictures, right? Selfies, if you wish. That's where they don't fly at 700 kilometers an hour. They don't go a mile away. And if they get lost, you can still find them yourself. Wi-Fi will happily do the job. But if you go a little bit more sophisticated, you could have a use case like a swarm of drones that are together inspecting a high-rise building for cracks in glass or stuff like that. Or agriculture, where again, you're covering a huge area, acres and acres of land. Those types of use cases could fit better to a private 5G network. We have also an engagement in the public safety sphere. Consider search and rescue in a mountain, where you actually want to have a swarm of drones that are interlinked, that are meshed together. One talks to the next to the one after, because there might not be coverage, right? It's that the operator might not have a cell tower on the mountain. Then you have, of course, the use cases where you have an extreme range, far away distances, flying over water. That's a whole other kettle of fish. So absolutely, the requirements are different across the range.
And what happens if communication is interrupted? Are there safety requirements or fail-safe mechanisms that developers need to think about?
You mean besides chasing your kid in the summer in Texas and walking into your neighbor's party?
Unless it's a really large drone.
That's actually, that is a very good point. Jokes aside, the FCC actually has rules and regulations for that. So it is, top of my head, it is weight-based. If it's below half pound or whatever, you are allowed to fly it we're in Austin, right, over ACL to take a selfie. But if the drone is large enough, you start getting into what you're allowed and not allowed to do and getting permits, etc., etc. So that is absolutely a thing. And the fail-safe piece to that, it comes with it. To prevent having to chase your kid in Texas, one obvious thing to do is add a GPS to the drone and tell the GPS to find its home point, either where you departed from or an address, whatever it is. That homing instinct is triggered when the communication link is lost. The drone knows, like, hey, I'm not hearing anything from the controller for 20 seconds. whatever it is. When that happens, go home by yourself. Then, of course, you're challenged because in that case, you rely on GPS, and GPS doesn't always work. And that's not necessarily like a jamming type of scenario, but GPS does not work on the ground. So if you're in a tunnel, doesn't go. GPS may have limited performance when you're in a forest or something like that. And what's called urban canyons. So if you're downtown Austin, there's so many reflections between the building that the actual GPS signal might not be perfect. You don't notice it on your phone because your phone has other ways of figuring out where it is. But GPS is not always perfect. So then you can go a little bit more sophisticated. You do geolocation by other means. Now you can, for example, look at cell towers around you and triangulate. If you know where 3 masts are from 3 different operators and you know their signal strength, you can make a pretty educated guess on where you are. All of that comes down to that home point thing. What you see on top of that is that instead of the link breaking, interrupting, Bridgette, as you said, you see preferably a gradual fail. So you go from HD video quality to VHS to black and white. And the operator typically is clever enough to kind of turn around when the image goes bad. So you may want to just prevent a fail-safe altogether.
All right, so now that sounds like a lot of complicated requirements for the developer to handle. From what you've talked about, like latency, long range, the reliability, throughput of the data. You talked about 2 different, control and video, and then the safety. These developers have to manage all these different use cases. You kind of touched on it before, but why can't the developers just use Wi-Fi, Bluetooth, or like a sub-gig? Why are you continually pushing for these different non-standard wireless technologies?
In fact, we see a lot of customers doing all of the above. It's not necessarily that they're stepping away from Bluetooth and Wi-Fi, but we said it right. It's all about the use case. Think, for example, not about Wi-Fi per se for that communication link, but you have the use of Wi-Fi as a wireless link when the drone is on the ground. When you want to extract a video, just like from an expensive camera that you may have at home, instead of plugging in a USB wire and finagling with that, Wi-Fi is used in drones just for firmware updates, image download, etc. We see ultra-wideband, another great NXP technology, used for precise positioning when a drone needs to land. If you have, for example, a remotely stored drone that is in agriculture or forest supervision, whatever, that is wirelessly charged as well, just like your phone is wirelessly charged. When the drone lands, it needs to be perfectly on that wireless charging spot within a centimeter. And ultra-wideband is used there. And you're right, sub-gigahertz ISM band is often used for the control from controller to the drone, the up, down, left, right, where the bandwidth is low, but because it's sub-gigahertz, you have much better range. It actually works, which is kind of important.
Before we started recording, you talked about software-defined modems. Once you step away and you're looking for other alternatives, the product from NXP, the LA9310, when does that come into the picture?
Yeah, that's my baby, my favorite chip, I think. It is specifically built to implement custom communication links, right? Every time we've spent like 15 minutes talking about crazy use cases and different technologies that solve different problems. That is, by virtue of being customizable, the LA9310 is made to do exactly that. We see that there is not a single waveform or modulation type or even RF frequency or RF bandwidth that dominates the market. Given that there is that level of fragmentation based on use case and it being a relatively new industry, it's really booming right now, we see a lot of innovation happening and different customers solving that comms link in a different way. We have customers that, for example, are doing something very 5G-like. That 9310 can happily run 5G. It could be a tweak on 5G to hit specifically private network. Or we have customers doing completely crazy stuff. Can't discuss it right now because they're working on patents and stuff like that. But completely out of the box, new waveforms that are specifically targeting the higher range, the higher Doppler, interference, jamming, and all kinds of scenarios. And that's where 9310 comes in. It is a DSP-driven architecture. And the tooling of all of this is out there and open. You can go to nxp.com, get the reference manual, compiler, etc., and write your own waveform. That makes it good. And because it is software-defined, you get the second benefit of being able to choose your RF operating frequency and band.
So let's dig into this a little more. Software-defined modem sounds pretty impressive, but can you break down what it actually means for the developer?
With infinite freedom come many ways to get things wrong and many ways to burn quite a few weekends trying to do it right. What it translates to is that the customer somehow has to invent the waveform, develop the waveform, productize the waveform, test the waveform, and improve the waveform. They have to compare and contrast that against buying something off the shelf from NXP or otherwise. This is where we plug in a network of NXP partners. These are either NXP customers that themselves sell their solution into the broader market, or hardware software development partners that, in case you don't want to write DSP code, they will write the DSP code for you. You just spec what you want to have. And of course, the open source ecosystem. We have what's called open air interface 5G waveform running exactly on this DSP. And if all of that fails, we are actually talking generative AI to do some of that coding faster, better, and cheaper for you. It wouldn't be a podcast if it wouldn't have AI in it somewhere.
That's right. Well, very cool. And for the software-defined approach, can it adapt to different frequency bands, regulations, protocols, or performance requirements? And what types of drone applications benefit the most from this flexibility?
Absolutely. It even gets worse, right? All these regulations are geographically unique. The US has different rules and regulations than Europe has, and so on and so on. The software-defined radio gives you the freedom to work inside, or if you wish, outside any of those regulations, protocols, and performance boundaries. That kind of also implies that the super cheap hobby drone market probably doesn't extract all the benefit from this approach. But for those customers that aim, for example, for private 5G, that is in the CBRS band in the US, but has slightly different frequencies in Europe, this type of stuff, I think, is, I'm not going to say the only solution, but pretty unique. Mm-hmm. That customization is hugely beneficial. For example, that 5G approach, the fully custom link for extremely long range, what we are seeing now, the mesh networking, the drone swarm, and high speed type of stuff. Those are the type of areas where this plays.
Yeah, so those drone swarms, you keep bringing it up. You're getting me nervous, Wim. So maybe we should talk about that some other time.
Light shows, man. Light shows. You said it.
Yeah, so it already exists.
It's a thing. It's a thing.
All right. Well, why don't you provide a little bit more details on the software? You talked about the DSP device, but what software do the listeners need to understand? If they're looking to build their own professional drone, like you said, those higher end drones, what does that communication stack actually look like?
Yeah, if you go back to the textbook, any communication stack is defined by what's called OSI layers. At the bottom, you have the physical layer, as you should remember from school. That is all the analog stuff, like power amplifiers, low noise amplifiers, filters, antennas, and that. But also the most mathematically intense portion of the processing chain, the digital processing chain. So typically, on the receive side, you have an antenna, low noise amplifier, filter, analog to digital converter, and then the DSP, digital signal processor. This is the difficult bit. If you have either a traditional single carrier link or a 5G derived over DMA link, there's a ton of very compute intensive processing. That is what happens at that lower OC layer in the DSP. That's the part that's, of course, the hardest to program. And this is where the innovation happens.
All right, so for the listeners, the OFDM, that's... orthogonal frequency division multiple access of DMA. That's the 5G
waveform.
Okay, all right. Just a fancy way of getting multiple channels on the same.
You hit it.
Okay.
It kind of ties back to that changing channel that we talked about. The way this works, super simplified, is you chop your band into 500, 1,000 tiny little sub-bands that you each treat individually. And that maps to a ton of math, because the way you do the chopping up, you do by means of FFTs. So now you're doing a gazillion FFTs. And guess what? The LA9310 is extremely good at doing gazillion FFTs.
I think that's what DSP stands for.
Digital signal processing. You got it. It's simple.
Right.
We don't need the textbook anymore.
No, we'll just bring Wim along.
On top of that physical layer, you then have the MAC layer. This is where you match up the stuff that goes into your FFT to what you're trying to transmit. If I build a video link from a drone down to Earth, I have a camera. After the camera, I have image signal processing. Allow me to plug the NXP out of the MAX processor here. The image signal processing is followed by a hardware accelerated H.264, H.265 encoder. And that encoder spits out frame buffers. So the job of the MAC layer is to match up those frame buffers to the FFTs. And that's chopping up, padding, adding headers, and making smart choices on what happens if it goes wrong. For example, a video link, if one of those frames got lost, what do? Do I just drop it, or do I retransmit it? Retransmission adds latency, and the so-called glass-to-glass latency, so from camera to operator, is key. So you have all those decisions to make. That's the MAC layer, the next one up in the protocol stack.
Once the customers are understanding the PHY, the MAC, they've chosen our products, what do they use as far as tools and enablement? How does NXP get them started working with these solutions?
First of all, as I said, open source is key in this industry. We have compilers, debuggers, reference manuals, example code, and all that stuff on nxp.com, GitHub, etc., etc. Just Google LA9310 and chase from there. We also support, on the software side, I mentioned a little bit earlier what's called open air interface. So that's a open source 5G stack. And again, just Google it, you'll find it. Then on the hardware side, whilst there is, of course, an NXP RDB, like for any other chip, we specifically worked, again, with the open source crowdsourcing community, companies like RFNM and Line Microsystems, to enable the hardware in that way.
Okay.
That's good, because with those efforts come communities, Discord servers, and more people that are working together. It's that collaboration that makes it work. And on top of that, recognizing that DSP is such a pain in the butt to code, we actually have a full pre-programmed physical layer that just works, leaving the MAC layer to do by customers, partners, etc. So there's a bunch of options, a menu if you wish.
All right, but now you did mention something earlier in your comments. I'm kind of leading you to talk about the AI. You mentioned maybe some of this difficulty with the DSP is being solved with some of your efforts there.
It is. We, just like everybody else, we need to jump on the AI bandwagon. Because a lot of this documentation and reference code is open source, we are now capable, or anybody, including us, is now capable of effectively, let's call it, it's not the right word, but let's say pre-training Claude to know our chip and our software. We actually went through that effort to speed up the design work. We haven't really pushed that out to the community yet. You'll see it come. But the idea is now that instead of writing your FFT by yourself, Claude will do it for you. And then compress the turnaround cycle to optimize, improve, and enhance that link. Ideally, at some point, I would like to see a competition between universities on who can build a better waveform. If you can do 10 miles, can I do 15? That would be an awesome experience. We're not there yet. But
Is that your retirement plan, to be a judge?
you think I'm old enough to retire? So yes.
Just giving you a hard time, but. So last question for you, Wim. Are there opportunities in robotics, industrial automation, autonomous vehicles, remote monitoring, or other safety systems that we're seeing? And for listeners who want to learn more or start evaluating these solutions, where should they begin?
The big one is robotics. That's another hot topic these days. If you look at a humanoid or a forklift, anything that is non-stationary robot. Those things have to obviously communicate with the internet or central office type of location. A lot of those problems are similar, right? If you have a humanoid walking through, let's say, an IKEA type of store, indoor and outdoor, those problems resonate, right? That's very similar to flying a drone for security of said store. The trade-offs are to some extent comparable to what we see in drone. However, it can go further because you can look at it in a different way. Within itself, the humanoid or the robot needs to communicate. And whilst you can do that with wires can be snapped, they can break, they're not always the best solution. So you can start wondering whether you want to wirelessly communicate within the robot. Does my robot brain talk to my pinky robot finger through wires or not through wires? That is another point-to-point, point-to-multi-point communication link with similar types of trade-offs and similar potential for innovation. I don't want to dictate here what that's going to look like, but there's a lot of work to be done, and that kind of makes it cool.
Definitely cool. Or, you know what? I just had this vision of all these humanoids walking dogs in the neighborhood, and they get lost and they disconnect and they all huddle together because they don't have the NXP DSP.
Yeah,
so
that's
we're
it.
going to prevent humanoids from clumping up on the corner of the neighborhoods. So, great.
Exactly.
All right, Wim. Well, thank you so much for joining us today. This has been a lot of information, helping us understand those unique requirements for professional drones to communicate. It's not as simple as those Wi-Fi and Bluetooth connections. It's not going to cut it for the breadth of opportunities and applications.
What really stood out to me is that drone communication isn't just about range. Developers are balancing throughput, latency, reliability, interference, safety requirements, and evolving regulations. Long laundry list there, all while creating or trying to create systems that can operate in the real world. Many of those same communication challenges extend well beyond drones into robotics, industrial automation, remote monitoring, and other edge applications.
Wim, again, thank you so much for joining. What is one thing that you want listeners to remember?
Thank you very much for having me. What I would take away from this is that when you're building something like a drone, a robot, or whatever other connected edge device, the communication piece is the foundation that makes it work or makes it fail. Start early on thinking through what are the requirements and what is the solution. Does a standard solution fit? Do you need to go proprietary? And adapt quickly to those requirements. I've seen it time and time again that things change because you learn. And that's great. It helps us sell flexibility, but it's the right answer to these kind of problems.
Wonderful advice, wise Wim. And for those listening and interested in learning more, we'll include links to the LA 9310 software resources and developer enablement materials in the show notes.
And if you enjoyed this episode and you didn't feel like we were just droning on and on about drones, make sure to subscribe, follow, and share this EdgeVerse Techcast, maybe with a fellow engineer or a friend. And if there's a topic that you want Bridgette and I to cover or an expert that you want us to invite like Wim, we'd love to hear from you in the comments.
Thanks again to Wim, or Wise Wim, for joining us. And thanks to all the listeners for spending time with us today.
Thank you. Super appreciate it.
And until next time, everyone, keep building, keep connecting and communicating, and we'll see you on the next episode of the EdgeVerse Techcast.